There is a moment buried deep in the history of science when reality stopped behaving the way we expected. It wasn't loud. There was no explosion, no sudden collapse of certainty. It happened quietly, in equations scratched onto paper, in experiments so small they could fit on a tabletop. And yet, in that moment, something unsettling became impossible to ignore. The universe, at its most fundamental level, does not seem to exist in a definite state until it is observed. Not measured in a dramatic sense, not interfered with violently, simply observed, as if awareness itself plays a role in deciding what is real. For centuries, physics had been the ultimate authority on objectivity. A world governed by laws that cared nothing about human thought. Planets moved whether we watched them or not. Stones fell whether anyone noticed. Reality was assumed to be complete, self-contained, and independent of consciousness. But quantum mechanics shattered that assumption. It introduced a universe where probabilities replace certainties, where particles exist in multiple states at once, and where the act of observation appears to select one reality from many. This is not mysticism. This is not metaphor. This is experimental physics. And yet, the implications cut far beyond physics. They reach into philosophy, neuroscience, and the nature of consciousness itself. If observation plays a role in shaping reality, then what exactly is the observer? And what does it mean to be conscious in a quantum universe? Tonight, we begin at the edge of what we know and step carefully into what we don't. If you're drawn to deep, thoughtful explorations of science and the universe, subscribe to the channel, like this video, and leave a comment. Tell us which part of the country you're watching from. At the dawn of the 20th century, physics appeared nearly complete. The laws of motion described by Isaac Newton had reigned supreme for over 200 years. James Clerk Maxwell's equations unified electricity, magnetism, and light into a single elegant framework. The universe seemed understandable, predictable, and fundamentally objective. Many leading scientists believed that all major discoveries had already been made, and that the future of physics would consist mostly of refining measurements and adding decimal places. That confidence did not survive long. The first cracks appeared not in grand cosmic questions, but in small, stubborn experimental anomalies. When physicists attempted to understand how objects emit light and heat, classical theories began to fail. According to established laws, a heated object should radiate infinite energy at short wavelengths. This absurd result, later called the ultraviolet catastrophe, was not a philosophical inconvenience. It was a mathematical disaster that contradicted experimental reality. In 1900, Max Planck introduced a desperate solution. He proposed that energy is not emitted continuously, but in discrete packets he called quanta. Planck himself did not fully believe the physical reality of this idea. It was a mathematical trick, a way to make the equations work. But the trick worked too well. It matched experiments perfectly. 5 years later, Albert Einstein took the idea seriously. While studying the photoelectric effect, he proposed that light itself behaves as if it is made of particles, later called photons. This explained why light below a certain frequency cannot eject electrons from metal. No matter how intense it is, energy at the smallest scales seemed to come in indivisible units. What followed was not a gradual adjustment, but a complete rethinking of what physical reality is made of. Over the next 3 decades, physicists discovered that electrons behave like waves, that particles can exist in superpositions of multiple states, and that fundamental outcomes cannot be predicted with certainty, only probability. The most disturbing implication was not randomness itself. It was where randomness appeared to enter the picture. In classical physics, uncertainty is a matter of ignorance. If you don't know the position of a planet, it's because you haven't measured it precisely enough. In principle, perfect knowledge would eliminate uncertainty. Quantum mechanics does not allow this. The uncertainty is not in our measurements. It is in the fabric of reality. Werner Heisenberg formalized this idea in 1927 with his uncertainty principle. Certain pairs of physical properties, like position and momentum, cannot both be known exactly at the same time. The more precisely one is defined, the less precise the other becomes. This is not due to technological limitations. It is a fundamental feature of the universe. But even this was not the most radical idea. The true shock came from the role of measurement itself. Consider an electron traveling through space. Quantum mechanics describes it not as a tiny billiard ball with a definite position, but as a wave function. This wave function encodes a range of possible positions, each with an associated probability. Before measurement, the electron does not have a single, definite location. It exists in a superposition of possibilities. When a measurement is made, something extraordinary happens. The wave function appears to collapse. The electron is found in one specific location, and all other possibilities vanish. The theory does not describe this collapse as a gradual process. It happens instantly without a clear physical mechanism. This raised an unsettling question. What exactly counts as a measurement? Early interpretations treated measurement as a physical interaction with a macroscopic device. A detector clicks, a screen lights up, a mark appears on photographic film. But this explanation quickly runs into trouble. Measuring devices are made of atoms, and atoms obey quantum laws too. If everything is quantum, where does the boundary between quantum and classical lie? This problem became known as the measurement problem, and it has never been fully resolved. One of the most influential attempts to make sense of this mystery came from Niels Bohr, a central figure in the development of quantum theory. Bohr argued that quantum mechanics does not describe reality as it is, but only what we can say about reality. According to this view, the wave function is not a physical object, but a mathematical tool that encodes our knowledge of a system. In this interpretation, questions about what exists before measurement are meaningless. Reality is not something waiting to be revealed. It is something that becomes defined through interaction. Albert Einstein found this deeply unsatisfying. He believed that physics should describe an objective world that exists independently of observation. In a famous exchange with Bohr, Einstein argued that the moon does not cease to exist when no one is looking at it. Bohr reportedly replied that such statements lie outside the domain of physics. The disagreement was not merely philosophical. It went to the heart of what science is supposed to do. Einstein, along with Boris Podolsky and Nathan Rosen, attempted to show that quantum mechanics must be incomplete. In 1935, they published a thought experiment now known as the EPR paradox. It involved pairs of particles that interact and then separate. Quantum mechanics predicts that measurements on one particle instantly determine the state of the other, no matter how far apart they are. Einstein famously referred to this as spooky action at a distance. He believed it violated the principle that information cannot travel faster than light. To him, this implied that the particles must carry hidden information that determines their behavior in advance. Decades later, experiments based on John Bell's inequalities tested this idea. The results consistently supported quantum mechanics and ruled out a large class of hidden variable theories. Nature, it seemed, really does allow correlations that defy classical intuitions about space, time, and locality. At this point, physics faced a choice. Either accept that reality is fundamentally non-local, probabilistic, and dependent on observation, or radically revise the theory. Most physicists chose acceptance, at least in practice. But acceptance did not bring clarity. The mathematical formalism of quantum mechanics works with astonishing precision. It predicts experimental outcomes to more decimal places than almost any other theory in science. Yet it offers no consensus on what is actually happening beneath the equations. Different interpretations attempt to fill this gap. The Copenhagen interpretation associated with Bohr treats the wave function as a tool for calculating probabilities. The many worlds interpretation proposes that all possible outcomes occur, each in a separate branch of the universe. Objective collapse theories suggest that wave functions collapse spontaneously, independent of observers. Pilot wave theories introduce hidden variables guided by a quantum field. Each interpretation preserves the mathematics while offering a different picture of reality. None can currently be distinguished by experiment. And this is where consciousness enters the story. In the early days of quantum theory, some physicists speculated that consciousness itself might play a role in the collapse of the wave function. The idea was not that human thought magically alters reality, but that observation, in the sense of conscious awareness, completes the measurement process. John von Neumann formalized this line of thinking by showing that the quantum description can be extended from particles to measuring devices, and even to the observer's brain. If the chain of quantum interactions never breaks, then collapse must occur at the level of conscious experience. This suggestion was deeply controversial. Many physicists rejected it outright, viewing it as an intrusion of philosophy or psychology into physics. Others treated it as an open question. Importantly, modern quantum mechanics does not require consciousness to function. Experiments work perfectly well without invoking observers with minds. Automated detectors record data just fine. The theory does not specify that a human must be present. However, the deeper question remains unresolved. What transforms a superposition of possibilities into a single experienced outcome? Decoherence theory provides part of the answer. When a quantum system interacts with its environment, its coherent superpositions become effectively unobservable. The system appears classical. Decoherence explains why quantum effects are not seen at macroscopic scales, and why measuring devices yield definite results. But decoherence does not explain why one outcome is experienced rather than another. It explains the loss of interference, not the selection of reality. This distinction is subtle but crucial. At the same time, neuroscience has struggled with its own foundational mystery. Consciousness, like quantum collapse, resists reduction to simpler components. We can map neural activity, identify brain regions associated with perception and awareness, and correlate mental states with physical processes. Yet the subjective experience itself, the feeling of being aware, remains unexplained. Some researchers have proposed that this is not a coincidence. One of the most discussed modern theories linking quantum mechanics and consciousness is the orchestrated objective reduction model, developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. This theory suggests that quantum processes occur within microtubules inside neurons, and that consciousness arises from orchestrated quantum state reductions. The theory is controversial and remains speculative. Critics argue that the brain is too warm and noisy for delicate quantum states to persist. Supporters point to emerging evidence of quantum effects in biological systems such as photosynthesis and bird navigation. It is important to be clear, there is no experimental proof that consciousness depends on quantum mechanics in this way. The theory is an attempt to address a gap, not a settled conclusion. What is undeniable is that quantum mechanics forces us to confront the role of observation in an unprecedented way. In classical physics, observation reveals reality. In quantum physics, observation helps define it. This does not mean that reality is created by belief or intention. Quantum outcomes follow precise statistical laws. No experiment has shown that human desire can override probability distributions. The universe is not manifesting wishes, but the observer effect reminds us that the act of measurement is not passive. It is an interaction, and interactions matter. As we move forward in this series, we will explore what quantum consciousness means, what it does not mean, and why it has captured the imagination of scientists, philosophers, and the public alike. We will separate rigorous physics from speculation, and examine how far the science actually goes. For now, what matters is this: the universe is not the clockwork machine we once believed it to be. At its foundation, reality is probabilistic, relational, and deeply strange. And whatever consciousness ultimately turns out to be, it exists within that strangeness, not outside it. The story of quantum consciousness begins not with answers, but with a realization that the more precisely we understand the physical world, the more it challenges our assumptions about what it means to observe, to know, and to exist. By the middle of the 20th century, quantum mechanics had proven itself beyond doubt. Every prediction it made was confirmed. Every alternative that tried to replace it failed. Transistors, lasers, MRI machines, atomic clocks, and the entire digital world were built on its equations. And yet, beneath this extraordinary success, a quiet discomfort remained. Physicists could calculate outcomes with astonishing accuracy, but they could not agree on what those calculations meant, especially when it came to the observer. In classical science, the observer is irrelevant. You can remove the scientist from the experiment, and the laws remain the same. The universe runs whether or not anyone is watching. Quantum mechanics refuses to cooperate with this assumption. The observer cannot be cleanly separated from the observed. The very act of measurement changes the system in ways that cannot be undone or ignored. This is not a philosophical exaggeration. It is built directly into the mathematics. The wave function, the central object of quantum theory, does not describe a single outcome. It describes a range of possible outcomes. Before measurement, a particle does not have a definite position, momentum, or state. It has probabilities. After measurement, it does. Something discontinuous happens between those two descriptions, and the theory itself does not specify how or why. This is where the observer enters the picture, not as a mystical force, but as a necessary component of the framework. One of the most famous demonstrations of this problem is the double-slit experiment. It is often simplified, misunderstood, and misused, but when examined carefully, it reveals exactly why the observer effect is so unsettling. When particles like electrons or photons are fired one at a time through two narrow slits and allowed to hit a screen, they produce an interference pattern. This pattern can only be explained if each particle behaves like a wave and passes through both slits simultaneously. But when detectors are placed at the slits to determine which path the particle takes, the interference pattern disappears. The particle behaves like a localized object instead of a wave. The critical point is not that measurement disturbs the particle. Any interaction would disturb it. The critical point is that the availability of which path information is enough to change the outcome. Even if no human looks at the data, even if the information is recorded and immediately erased, the interference vanishes. Reality behaves differently depending on whether information exists in principle. This forces a radical rethinking of what observation means. It is not about eyes or awareness in the everyday sense. It is about the structure of information in the universe. Measurement is not simply learning something that was already there. It is an interaction that defines what can be said to exist. John Wheeler, one of the most influential physicists of the 20th century, pushed this idea further. He proposed the concept of the participatory universe. In Wheeler's view, the universe is not a fixed entity evolving independently of observers. Instead, observers are active participants in bringing the universe into being, at least in the sense of defining its history through measurement. Wheeler illustrated this with delayed choice experiments. In these setups, the decision to observe a particle's wave, like behavior is made after the particle has already passed through the experimental apparatus. Astonishingly, the outcome still depends on that later choice. It is as if the particle's past behavior is not fully determined until it is observed in the present. These experiments do not allow communication backward in time, and they do not violate causality in any practical sense. But they do challenge the classical idea that the past is fixed and independent of future observations. Wheeler summarized this with a provocative phrase: "No phenomenon is a real phenomenon until it is an observed phenomenon." This does not mean that the universe did not exist before observers. Wheeler was careful to avoid that interpretation. Rather, it means that the universe we describe, the universe with definite properties and histories, is inseparable from the network of observations that define it. At this point, many physicists retreat to a pragmatic stance. Quantum mechanics works. Interpretations are optional. Shut up and calculate. This attitude has been enormously productive, but it leaves a vacuum where understanding should be. Into that vacuum, ideas about consciousness inevitably flow. The word observer sounds psychological. It suggests awareness, perception, experience. Even if physicists insist that observation does not require a mind, the language itself invites deeper questions. If the theory depends on observation, and observation is ultimately tied to experience, then consciousness cannot be entirely irrelevant. This is not an argument, it is a tension. Some interpretations attempt to eliminate the observer altogether. The many worlds interpretation, proposed by Hugh Everett in 1957, denies wave function collapse entirely. According to this view, the wave function always evolves smoothly according to the Schrödinger equation. When a measurement occurs, the universe splits into branches, each corresponding to a different outcome. In one branch, the particle is here. In another, it is there. The observer becomes entangled with the result, experiencing only one branch. In this picture, consciousness does not collapse the wave function. It simply follows one branch of a constantly branching multiverse. The observer effect is reinterpreted as an illusion arising from entanglement. Many physicists find this elegant. Others find it extravagant. It replaces one mystery with an infinity of unobservable universes. Whether this is a virtue or a flaw remains a matter of debate. Other approaches go in the opposite direction. Objective collapse theories propose that wave functions collapse due to physical mechanisms that are not yet fully understood. These collapses happen spontaneously, with probabilities that increase as systems become larger. Consciousness plays no fundamental role here. Measurement outcomes become definite because nature itself enforces definiteness. These theories are testable in principle, and experiments are underway to look for deviations from standard quantum mechanics at large scales. So far, no clear evidence has been found. Still, other interpretations, such as relational quantum mechanics, argue that properties are not absolute but relative. A system does not have a state independent of other systems. Instead, states exist only in relation to observers. Different observers can legitimately describe the same system in different ways without contradiction. This idea dissolves some paradoxes but raises others. If reality is relational, what anchors it? What prevents it from dissolving into pure subjectivity? At this point, it becomes clear that quantum mechanics is not just a theory of particles. It is a theory about information, relationships, and limits. It tells us what can be known, how it can be known, and under what conditions knowledge becomes meaningful. Consciousness enters the discussion not because quantum mechanics proves anything about the mind, but because both face the same kind of explanatory boundary. Consciousness is not observable from the outside in the same way particles are. It is known directly only through experience. Physics describes the world in third-person terms. Consciousness is first person. Bridging that gap is one of the deepest challenges in science. Some researchers argue that consciousness is an emergent phenomenon, arising from complex information processing in the brain. On this view, there is nothing fundamentally mysterious about it. Given enough neurons arranged in the right way, subjective experience appears. Others argue that this explanation is incomplete. Information processing alone does not explain why there is something it feels like to be conscious. It explains behavior, not experience. Quantum theories of consciousness attempt to address this by suggesting that consciousness is tied to fundamental physical processes rather than emergent complexity alone. These theories are controversial, and none are widely accepted. But they persist because the standard frameworks leave something out. It is essential to draw a clear boundary here. Quantum mechanics does not say that consciousness creates reality. It does not say that thoughts control particles. It does not say that belief determines outcomes. These ideas belong to metaphysical or spiritual interpretations, not to established physics. What quantum mechanics does say is more subtle and more unsettling. It says that the universe does not come with all its properties pre-installed. Some properties become defined only through interaction. Measurement is not a passive act of reading a value. It is an active process that brings certain possibilities into focus while excluding others. In everyday life, this distinction does not matter. Tables remain solid. Cars remain in place. The world behaves classically because quantum effects are suppressed by decoherence. But at the deepest level, the classical world is an approximation. This realization forces a shift in perspective. The observer is not a ghostly influence hovering outside the universe. The observer is a physical system embedded within the universe, interacting with other systems. Observation is just another physical process, but one with unique consequences. In this sense, the observer effect is not about consciousness in isolation. It is about participation. Every act of measurement is an act of participation in the unfolding of reality. John Wheeler took this idea to its logical extreme. He suggested that the universe is self-excited, that observers arise from the universe and in turn define the universe through observation. A loop, not a hierarchy. No privileged starting point. No final external vantage. This is not a settled scientific theory. It is a philosophical interpretation inspired by physics, but it captures something essential about the modern view of reality. The sharp line between subject and object, observer and observed, has eroded. The observer cannot be fully removed from the description of nature. Not because humans are special, but because information is relational. Facts are not free-floating. They are always facts for some system relative to another. This idea has practical consequences. Quantum information theory, one of the most active fields in modern physics, treats information as a physical quantity. Entanglement, superposition, and measurement are resources that can be quantified, manipulated, and exploited. Quantum computers operate by controlling these features, not by avoiding them. In this context, the observer effect is no longer a philosophical nuisance. It is a tool. Yet the deeper questions remain. Why does a particular outcome occur? Why this experience and not another? Why a single world of experience emerges from a mathematical structure that allows many? These are not questions quantum mechanics answers. They are questions it exposes. As we move forward, the temptation is to fill the gaps with certainty, to declare that consciousness collapses the wave function, or that the multiverse is real, or that reality is purely subjective. Each of these claims goes beyond what the evidence supports. What is clear is that the observer effect is not a trick of language or a misunderstanding. It is a real, experimentally verified feature of the world. It tells us that the universe is not simply there, fully formed, waiting to be looked at. It is revealed through interaction shaped by information and constrained by limits that we are only beginning to understand. Quantum consciousness is not a claim that the mind controls reality, nor that the universe bends to belief. It is something quieter, deeper, and far more unsettling. Modern physics tells us that reality, at its most fundamental level, is not a collection of fully formed objects moving through space and time. It is a structure of possibilities, probabilities, and relationships that only become definite through interaction. The observer effect does not elevate humans to cosmic creators. It dissolves the illusion that observation is passive. Measurement is participation. Knowledge is not extracted from the universe without consequence. Every act of observation draws a boundary, selects an outcome, and defines what can be said to exist. Consciousness remains unexplained, not because science has failed, but because it has reached a boundary. Neuroscience maps the brain with extraordinary precision, yet subjective experience still resists reduction. Quantum mechanics predicts outcomes flawlessly, yet offers no consensus on how a single experienced reality emerges. These two mysteries do not prove they are the same problem, but they point toward the same limit of understanding. What we know is this: the classical world we experience is an approximation, stabilized by decoherence and scale. Beneath it lies a universe where certainty dissolves, where outcomes are not fixed in advance, and where the observer cannot be cleanly removed from the description of nature. This does not make reality subjective. It makes it relational. The most honest conclusion is also the most uncomfortable one. We do not yet know whether consciousness is fundamental or emergent, whether the universe requires observers or merely permits them, or whether the deepest structure of reality is informational, physical, or something not yet named. But we do know this: the universe is not indifferent to how it is questioned. And in trying to understand it, we are forced to confront something equally profound: the limits of what it means to observe, to know, and to exist inside the system we are trying to explain. That is the true lesson of quantum consciousness. Not certainty, not control, but humility before a universe that reveals itself only through interaction and never all at once.